Hi guys, my name is Gloria and I'm here with Courtney and we're going to go over our ENGI-460 Presentation 2. Alright, so we are going to go over what it means to evaluate an integral. So the one that we're going to be using for this demonstration or for this example is y equals x or f of x equals x, which is very simple. And so in these terms, when there's just an x and a y, the integral means the area underneath the curve. So this is very simple. This is just underneath this straight line. So it says on support 0 to 5, so we're only going within this 5 by 5 square right here. And so if you remember geometry, the area of a triangle is the base times the height divided by 2. B times h over 2 or times 1/2. And the base is 5 and the height is 5, and so that's 5 times 5. 25 divided by 2 is 12.5. And obviously this is very simple, but for the sake of using Monte Carlo now, we're going to use the uniform distribution. And since x goes from 0 to 5, if it was uniform, it would be 1/5 all the way through. And so when we factor out the function, we get 5x. And so what that really means is we're using the uniform distribution, and if we multiply the uniform distribution times 5x, we will get what? X, which is what our f of x is. And so that's really what we're going to be using in a little bit. So now we're here in MATLAB, and this whole top section is just the closed form for comparison. So our function is x, y equals x, and our integrals is the function from 0 to 5. And then we'll run this in a bit after I explain this part. So we clear the x, and this is just 10 million iterations. Obviously you could do more or you could do less, but this is a large enough number, but also doesn't take that much time. And the random uniform times 5, just because if I just did rand, it would just give me some kind of value between, obviously still uniform distribution, but between 0 and 1, but multiplying it by 5 will now give me something between 0 and 5, which is what I want. And then the 5 times x, which we talked about earlier, is a factored out function. Then we also take the standard deviation so that we can give a 95% confidence interval. And these lines here, the f print f, that is just formatting whenever we run it. So closed form, 12.5, as we saw earlier in calculating the area under a triangle. And the Monte Carlo estimation, this is actually pretty good. It's really good. That's the exact same thing. And the 95% confidence interval is that. But watch, if I run it again, it can be different. So see, that's a little bit larger. And if I had, say, less iterations, just 1,000, it can be way off. I mean, that's not necessarily way off, but not as good as it was before. So can't we just do the integration? Why would we do Monte Carlo when we actually did this 1/2 BH gave us the exact correct answer? Why are we even considering a simulation of data points? So this function is simple, but there are many complex systems. Say it's not 2D, it's 3D, 4D. So finding the integral closed form might be impossible, and if not impossible, very difficult. And now for the concept of expectation. This is basically the mean, which is the expected value. So say you had 10 children and there's the same probability of having a boy or a girl. The expectation would be to have 5 girls and 5 boys. Obviously that's a very simplified version of expectation.
So what is meant by a Monte Carlo as an integral estimation? The statement, we can estimate the value of any integrand no matter how complex the integrand, is important. Why? What relationships do integrations, probability densities, and fissionable materials have in common? Well, they are all complex, and a closed-form solution may not be found or easily found for them. So how can we use Monte Carlo to solve for complex distribution functions? Well, similar to the example that we just did, you would use a known distribution, factor it out, and then simulate using a large number of points. Then you calculate the mean, standard deviation, and provide the confidence interval. How are complex distribution functions related to the mathematics behind determination of the yields of fissionable, fusionable materials? Some examples are neutron gamma ray emission probabilities, nuclear decay processes, neutron multiplicity and probability, and they're all very complex functions that Monte Carlo can help solve. Alright, that's all we have for you. Thanks for watching.